Hello and welcome to yet another Korean College Scholastic Ability Test video, and welcome to yet another combinatorics video after such a long time since the last one. The problem says, how many ordered pairs of non-negative integers a, b, c, and d satisfy following conditions? Condition A plus b plus c minus d equals 9. And condition B, d is less than or equal to 4 and c is greater than or equal to d. Now, many people who see this problem for the first time will be quite puzzled, but students who were well prepared for this test would have immediately come up with a method: combinations with repetition. So how is this problem about finding the number of non-negative integer solutions somehow related to important mathematical concepts such as combinations with repetition? Well, to understand that, we have to take a look at simpler problem, but perhaps more common and thus more typical problem. So first, let us assume the easier case where d equals 0. Then the problem reduces to simpler version, which is find the number of non-negative integer solutions of a plus b plus c equals 9. In other words, how many of these ordered pairs of non-negative integers are there? And this is the part where combinatorics gets involved. You see, you can think of finding the non-negative integer solutions of this equation like this. First, let us think of these a, b, and c as some kind of distinguishable items rather than variables with certain values. Then let us think about the process of choosing 9 items out of these 3, but allowing the repetition, or duplication, or replacement, or whatever you want to call that. But we don't think about the ordering here. Then there are several different samples that you can obtain, for example, like this one, or this one, or this one. Let's just use these 3 examples. Here, the number of each letter is the value of that variable in a non-negative integer solution. In our first example, we have 3 a's, 3 b's, and 3 c's, which corresponds to the solution a equals 3, b equals 3, and c equals 3. In the second example, we have 2 a's, 4 b's, and 3 c's, which means a equals 2, b equals 4, and c equals 3. And in the final example, we have no a's, 5 b's, and 4 c's, which is the solution a equals 0, b equals 5, and c equals 4. Therefore, we can say that the number of non-negative integer solutions are number of ways of choosing 9 elements from a set having 3 elements, but with repetitions. And this is so straightforward that we can just straight up look for the most general case. So instead of 3, there are total n variables, and we want their sum to be k, which should be a non-negative integer. And we want to find the number of non-negative integer solutions to this equation. You can think of this process as choosing k items from a set of n items, allowing the repetition. Then the number of each variable is the value of that variable. So the number of solutions is given as combinations with repetition. More specifically, choosing k elements out of n elements. This number of combinations with repetition is denoted like this, with double parentheses. This expression is commonly read n multichoose k. But how do we calculate this n multichoose k? Well, it can be calculated using normal combinations. More specifically, it is n plus k minus 1 choose k. That is, the number of ways to choose k items from a set of n plus k minus 1 distinct items, but without repetition. The derivation is quite simple, so I will just quickly derive this formula right now. I have already explained that n multichoose k is equivalent to the number of non-negative integer solutions to this equation, so I will use this equation to derive this formula. And for that, let us think about another approach to find a non-negative integer solution. This time, I will consider this k as a collection of k identical items, such as these squares. If we consider an individual square as value 1, then we can think of this as the number k being split into ones. Next, let us prepare some bars here, but this time the number of bars is n minus 1, one less from the number of variables of the equation. What we're going to do here is by using these n minus 1 bars, we are going to separate these k squares into n different parts, where each part is separated from another by bars. Then the value of each variable is assigned as the number of squares in each part sequentially. Then boom, we have one solution to the equation. In our a plus b plus c equals 9 example, now there are 9 squares and 2 bars. And if we separate the squares like this, this corresponds to the solution 3, 2, 4. And if we separate like this, then this corresponds to the solution 0, 2, 7. Alright, so we have established that the number of non-integer solutions is the number of ways to arrange k squares and n-1 bars so that the squares are divided into n parts. Now, if we consider the total number of squares and bars, or the length of the resultant string, it will be n plus k minus 1. It means that we have n plus k minus 1 spots that can be filled with either squares or bars. Now, the process of arranging squares and bars can be done like this. First, we choose k spots and fill them with squares. And for whatever spots not filled with a square, we fill them with bars. So the number of k's is given as n plus k minus 1 choose k, choosing k different spots from n plus k minus 1 different spots. Or we can do it the other way. We can choose the spots for bars first, so we choose n minus 1 spots for bars. And then we fill the remaining spots with squares. Here, the number of cases is the number of ways to choose n-1 spots for bars from n plus k-1 spots, so it is n plus k-1 choose n-1. However, by this property of combination, it is essentially the same as n plus k-1 choose k. Therefore, we have proved this relation, and with this, we now have everything we need to solve the main problem. So let's get back to the main problem. Alright, so we are back at the main problem, but here we have an issue that in this first condition, we have minus d, and we have an additional condition that can make our lives more miserable. But we can actually use these second conditions to simplify the first condition. From this condition, it follows that c minus d is greater than or equal to 0. And in the first condition, we also have c minus d, so we can substitute this expression into something simpler, like this c prime. Then we have a plus b plus c prime equals 9, and a, b, and c prime are non-negative integers. Therefore, if the value of d is fixed to some value that satisfies this condition, then finding the number of non-negative integer solution of the original equation is equivalent to finding the non-negative integer solution of a plus b plus c prime equals 9. More specifically, the cases look like this. So from this condition, the possible values for d is 0, 1, 2, 3, and 4. And when d have these values, the original equation becomes these. And for each equation, we make these substitutions. Then we obtain these equations, and notice that the equations are all the same. Therefore, we only have to find out the number of non-negative integer solutions of this equation and multiply that number by 5. And the number of non-negative integer solutions to this equation is simple. It is the number of ways to choose 9 items from these 3, allowing repetition. Therefore, it is 3 multi-choose 9. And using this relation, it is 3 plus 9 minus 1 choose 9, so it is 11 choose 9, which is the same as 11 choose 2, so 11 times 10 over 2 times 1, so we have 55. And as I said before, we have 5 possible values for d, and for each d, we have 55 non-negative integer solutions, so the total number of disordered pairs is 55 times 5, which is 275. So from our multiple choice here, the correct choice is 3. And that's all for today's video. If you enjoyed this video, please check out this video of mine where I solve another combinatorics problem from the CSAT of another year. And don't forget to hit like and subscribe buttons. And as always, I will see you in another video.